Hello, this is Dr. Heidelberg, and our presentation today is microprocessors in mechatronics. We'll follow the reference textbook of Bolton, fourth edition, and the topics that we'll cover is including the microprocessor, microcontrollers, programming, assembly language, instructions, programs, and example. The microprocessors have basic definitions such as memory, RAM, read-only memory, PROM, programmable RAM, EPROM, erasable PROM, and electrical erasable PROM, and random access memory. The buses that the microprocessor is working with include the data bus, address bus, and the instruction bus. There are registers which are used for temporary memories, including the program counter, the memory address, the status and flags, instruction, stack pointer, and general purpose. We'll see a little bit more of these later on. The microcontrollers include microprocessor, CPU, as well as input-output modules and memory. The bits that go through the buses are either 0, 1. A quartet is defined as 4 bits or nibble. The byte or octet is 8 bits, and a word is which is 2 bytes or 16 bits. The example here of Motorola 6800 microprocessor has a 40-pin DIP package. DIP means dual inline package where 2 parallel rows of electrical connecting pins are lined up on 2 sides. We have 20 on each side. The architecture of the Motorola 6800 is shown over here. It has 8-bit data bus, and it has 16-bit address bus. It has accumulators, we'll see in a minute, and it has various input and output ports other than the address and the data. It has data bus enabled tri-state control where the microprocessor can disable this address and have external source going into the address. We have bus available signal, we have halt, we have non-maskable interrupt coming in, we have a reset terminal, we have timers and counters, we have read and write command to the peripheral equipment, and valid memory address as well as interrupt request. The registers of the 6800 are listed over here in a little bit more details. There are 2 accumulators, A and B. Each is 8-bit accumulator, which stores the temporary data that goes into the arithmetic and logical unit, ALU. Then there is an index register which stores the offset to the memory location. It has a stack program, a pointer, which contains the address of the next instruction. And then there's a program counter, which, I'm sorry, that the program counter connects the address to the next instruction, and the stack pointer contains the address of the top of the stack in the random access memory. There's also 8 bits of flags, such that the carryover, the overflow, 0, negative, and interrupt. And these pretty much highlight the registers of the 6800 microprocessor. The microprocessor is being manufactured on a silicon wafer. We see several of them shown over here on a wafer, which is like 0.5 millimeter thick from a wafer ingot, and it's being processed in a machine, which is called a stepper. And the principle of the stepper is shown over here. There is a light source that is focused through a lens. The lens shines through a photomask. The photomask has the pattern of the circuit on the chip, and the light is then being focused on the wafer. This being reflected on the silicon wafer, which contains millions of transistors, and mimic the pattern that was shined over here with the light through the photomask. Then the stepper moves, and as it moves, it prints all these various chips, which are identical to each other. And then the process separates them and assembles them on a PCB board. As we see over here, new IBM computer chips can hold 30 billion transistors on a very small size of a chip. So in the case of a microprocessor, the integration into a product is shown over here. The microprocessors is placed on a PCB with other equipment. This is the CPU, and then separate a card. There is a memory and another card for the I/O board, and then putting it in a chassis with a power supply, and then the result is a computer system. The microcontroller, on the other hand, as we saw earlier, includes a microprocessor CPU, as well as a memory and input-output port, all embedded in one chip. This is an example of Intel 8742, which is an 8-bit microcontroller, includes a CPU at 12 megahertz. It has 128 bytes of RAM. It has 2048 bytes of EEPROM, and I/O all on the same chip. We see the general architecture of a microcontroller is shown over here. It has an arithmetic logic unit, a random access memory, read-only memory, registers of various type, interrupt circuits, as we saw earlier, a timer, input-output ports, clock, which synchronize all the modules, stack pointer, and program counter. The Intel 8051 microcontroller, for example, has an Harvard architecture. As we see over here, we have the control unit, we have the arithmetic logic unit, data memory, instruction memory, and I/O module here. The advantage of the Harvard architecture is that there is efficient pipelining, where the operand for the instruction can be fetched and the instruction can be fetched, and they can be done simultaneously. There are separate buses for data and instructions, and it is tailored in construction towards FPGA. It's a gate array which is field programmable by the customer, meaning that it can be made as a custom chip. The disadvantage is not widely used, and it's more difficult to implement. Over here, we see the Intel architecture of the microcontroller. We see the arithmetic unit, a logic unit over here with temporary, temporary memory that receive the data from the bus, and then they provide the arithmetic or logic calculation. There are list of input and output ports over here. There is the oscillator that comes from a quartz circuit. There is the PSEN over here, which is a program store enable, and that allows to get an external memory. There is an ALE, which is address latch enable. And then what we see here that each one of these ports provides 8 bits, but the addresses are 16 bits, and therefore we need the latch in order to combine the two inputs from these two ports in case we combine them into a single address value. There is an external access program. When it's a bit of one, it actually is internal access to the program, and external program is fetched when the bit is 0. There's also a reset over here that when it is activated with 1, the timer over here is going to wait 2 cycles before it is going to start the microprocessor startup. There are 4 ports, port 0, port 2, port 1, and port 3. Each one has 8 bits. Each one of these bits can provide a signal. For example, bit 8 on port 0 could be used to turn on a switch of a motor, or bit 2 on port 1 can switch off a pump. There are also transmit and receive serial ports, which are controlled over here by this unit, and they can be delivered into port 3. There are various registers of address, instruction, counter, stack pointer, and a memory of RAM and temporary buffers and temporary storage locations. What we see over here that in the particular setup that we saw for 8051 architecture, port 3, for example, has multiple functions, not just data line, but also it has the read data, it has write data, control input, it has timers, it has 2 interrupts, and also the transmit and receive data pins. The definitions that we have in various programs that we use in order to control microprocessors are that the software is defined as a set of instructions. An instruction set is a collection of several instructions. A program is a series of instructions. A machine code is the lowest value level of programming, which is basically zeros and one at binary code. The mnemonic is a shorthand code. For example, add to accumulate A, whatever is in a certain memory location, which is right after this command. Assembly language is a shorthand coded language. The assembler program converts the assembly language into a machine code, and high-level languages like BASIC, C, Fortran, and Python are the ones which are mostly used in programming microcontrollers. In this view, we see the different levels of programming languages. The highest level, the lowest level is the basic hardware of electronic circuits. Then what operates this with logic is the machine language actually controls all this logic. Then the assembly language is a language which is written by the programmer and downloaded into the microcontroller, and it's been converted into the machine language, and then higher level languages like Fortran, C, and Pascal. And on top of it, visual languages like the MIT Scratch. We see that the programming process over here starts by defining the problem that we like to solve, defining the algorithm for the solution, constructing a flowchart, then translating the flowchart into a set of instructions in assembly, C, or Python, and then test and debug the program. The flowchart over here uses some symbols. We see the racetrack over here is used for start and end. We have over here the trapezoid is an input and output, such as an input, for example, from a cloud. And we have over here a decision, which like a diamond. If it is true, we continue. This is a designation of a process unit. And if it is false, then we branch out, for example, over here, and we end. The mnemonics for the assembly language are specific for the particular processor or microcontroller that we use. This particular one is for Motorola. And we see, for example, LDA is used for load the accumulator. LDX is load the index register. STA is store the accumulator. STX is store the index. Then we have register, transfer, tax, and tax-A. And then we have clear memory, arithmetic like add, subtract, multiply. We have the negate, in other words, taking the binary number and writing the exact inverse. We have incrementing the memory locations and Boolean logic. So there are quite a few of these, and this shows us an example of a flowchart and the assembly language program for adding two numbers. So we start the program, we load the accumulator with the first number, then we add the second number, we store it in memory, and then we stop. So what we have here is this column is for the label, this column for the code, this is the operand, and this is the comment separated with a semicolon. So we define over here the value in location number hexadecimal 00 as num1. We equate that. Num2 is value in this location. Then we define the sum will be stored in location 02 hexadecimal, and then we start the program over here. This is the origin of the random access memory. This is the program definition, and then we load the first number into accumulator A. We then add the second number into accumulator A, and then we save the sum into the storage location of which was defined as a sum, and then we end it. The assembly language has some advantages. The pneumatic replace instructions, and it is easy to write and understand in comparison to machine code. It's also useful to write in simple applications such as traffic lights. The disadvantages are that it is abbreviated and has a large number of mnemonics which are hard to remember. The program is written for a certain machine, so therefore they are cannot be interchanged. The program is less efficient than the machine language, and it is it's used by different ways by different manufacturers. So it is a non-standardized program. This completes our presentation, and we'll talk more about higher level programming such as C in our next lecture. Thank you.